Testing. Okay.
Hello and welcome to this IChemE Global Awards webinar. My name is Matt Dorker and I'm your host for today's presentation. The IChemE Global Awards celebrate chemical, process and biochemical engineering excellence and are widely recognised as the world's most prestigious chemical engineering awards. Today we'll be announcing the winner of the IChemE 2020 Industry Project Award, sponsored by Plastic Energy. This award recognises the best chemical engineering project undertaken in the last 3 years to be implemented in industry. But before we check out our finalists, please welcome our sponsor, Plastic Energy's Head of Policy and Sustainability, Chloe Rigaud.
Hello everyone, we're Plastic Energy. I'm Chloe Rigaud and I'm very delighted today to sponsor the Industry Project Award. So I'm going to start first by giving you a very quick overview of who we are and of Plastic Energy. So as you all know, today one of the key issues in the world has been the growing plastic problem. The growing plastic problem. So we see that there is a growing, obviously a growing production of plastic, and unfortunately only 14% of it is currently recycled worldwide, the rest being mainly incinerated or landfilled. There is a growing momentum to change that direction through the public, some restriction in terms of imports, and especially at the European level, some very strong policies to improve recycling and waste management, as well as voluntary commitment from various large companies. So here the question is, how does Plastic Energy support basically this change of direction and support the circular economy for plastic? So by basically transforming plastic waste into basically recycled oil, into hydrocarbon oils, what we are doing is supporting those targets to be reached and supporting the EU 55% recycling target by 2030 to be reached. So this is obviously in collaboration with existing mechanical recycling, but what we do is increase the recyclability of some plastic that are currently being incinerated or landfilled. So we basically complement the effort of mechanical recycling to recycle more plastics. Another advantage of our technology, of our chemical recycling technology, is very much that we can from there incorporate the recycled content into food grade products. So currently there is regulatory limitation to incorporate recycled content into food grade applications, and chemical recycling very much enables that. So now a little bit more about who we are. So we have a patented technology that has been developed for more than 10 years by our engineers in London. Importantly, we have 2 industrial plants in Almeria and Seville in Spain that have been industrial and commercial for the past and operating for the past 3 years, which very much gives us an edge because we are already producing this output to make new plastics. What we do with it is very much to produce hydrocarbon oils, sell it to the chemical industry. The idea is very much to replace this recycled oil, fossil oil, by this recycled oil to create new plastic, so to create recycled plastic. We have many partners with whom we're working, especially on the petrochemical side. So, for instance, SABIC, INEOS, Total, Petronas, and others. With those partners, we are aiming to very much develop the industry, and we're aiming by 2025 to have more than 10 chemical recycling plants, mainly in Europe. So here I want to show that we are beyond the demonstration and now at the commercialization of this plastic to plastic process. So Now we can see that in commercialized product on the European market, we can find some recycled content from chemical recycling. So that has come from, for instance, a mix of flexible plastic waste that has been transformed in our plants and has been put back in, for instance, Magnum product or Knorr product, as you can see on the left. And on the right, into the cheese wrapping of Bradbury that are being sold at Tesco. So as you can see, it is very much a new and very promising industry that can increase the recycling rates and the incorporation of recycled content into food grade packaging. Thank you very much, and don't hesitate to follow us on LinkedIn, Twitter, and Instagram.
Okay, thank you, Chloe, and thank you, of course, to our sponsor, Plastic Energy. So then, let's check out the finalists. We start with a joint entry by Cadent, Northern Gas Networks, Progressive Energy, the Health and Safety Executive, Keele University, and IChemE Power. Dow Consumer Solutions. A joint entry from Dow Europe and H&S Anlagen Technic. Dow Inc. Dow Silicons Belgium. A joint entry from Florence Energy, Mintra Energy, and MK Aromatics, Johnson Matthey, and Saudi Aramco. All our finalists have been invited to join us today to give a short presentation on their work, and subject to time, we'll be inviting you to participate in Q&A at the end of each presentation. You can ask your questions via the questions box in the GoToWebinar portal. We're also live tweeting throughout all of our Global Awards webinars. You can get involved using the hashtag IChemE Awards. But it's now time to welcome our first speaker. Please welcome Sikandar Mahmood.
Good morning, all. Excellent. I'm hoping everyone can see the presentation. So it's a pleasure to be able to present today and represent the High Deploy Consortium at the IChemE Awards amongst the other finalists. So yeah, my name is Sikandar Mahmood. I work for Cadent. We're the largest gas distribution network in the UK, and we're also the lead for the High Deploy project. So I'll just quickly go over the strategy in terms of decarbonisation and an overview of the High Deploy project itself, and then provide you with an update of where we are and what we're aiming to do next. So the majority of homes in the UK rely on natural gas to heat their homes and to use for cooking. And the UK has already made some significant strides in working towards decarbonisation of the gas supply, with the use of biomethane, bio-SNG, which looks at converting black bag waste into gas, and the various blending projects that are going on across Europe, which is what I will focus on in today's presentation. And all that work is leading towards progressively supplying closer to 100% hydrogen to selected consumers, such as heavy industry users, or using it for transport fuels and power generation. So why blend into the gas networks? First and foremost, it's a way to decarbonise without causing much disruption to the customers. So we're able to utilise the same appliances, the same materials and pipelines that we have in the network, and the same operational procedures. And whilst also doing that, we're providing a meaningful decarbonisation pathway. And we say if you were to do it across the UK, it'd be equivalent to taking off 2.5 million cars from the road. And it also gives us an opportunity to get hydrogen used in the homes and customers used to hydrogen. And High Deploy is the first project in the UK to do this, to get hydrogen in the domestic setting. And whilst we're building that evidence base, it allows us to develop a wider industry supply chain and increase the production capacity for hydrogen. In terms of the project objective and timeline, so the overall objective for High Deploy is to facilitate hydrogen blending across the UK and demonstrate that it can be done safely and efficiently. The High Deploy Consortium is formed from Cadence, Northern Gas Networks, Keele University, who are the host site, the Health and Safety Laboratory, providing all the scientific knowledge, IChemE Power, focusing on the electrolyzer, and Progressive Energy, providing support with overall project management. And we kicked off the High Deploy project in 2017, building the safety case for our first demonstration at Keele University. Due to COVID, that is still ongoing, and I'll touch on that a little bit later. And our second demonstration will be in the northeast of England, where we first build the safety case, do the installation, and start the live demonstration. And then, last but not least, we will have a final demonstration in the northwest of England. So in terms of the safety case, the UK has an excellent safety regime, and some rigorous evidence is needed to combat the gas safety management regulations, which currently stipulate that you can only have 0.1% mole hydrogen within the gas networks. So as the project, High Deploy was required to build that evidence on materials, for example, the pipelines that we have in the network and how they will operate on blended gas mixtures in comparison to natural gas. Looking at the gas characteristics, so how would gas accumulate in buildings and what would be the consequences if it was to ignite when you're comparing it to natural gas. We were evaluating the appliances and making sure boilers and cookers and fires can operate safely on blended gas mixtures. And quite importantly, researching the consumer perspective and implementing all that into the safety case so that we can achieve an exemption to those gas safety management regulations, which we successfully did. After an 18-month rigorous program, we managed to achieve the first exemption to the hydrogen limit within the GSMR regulations to allow us to carry out the live trial. So following the safety case, we started with the installation on site. We did some testing of all the equipment prior to bringing it to the Keele University site. So these pictures here are just showing the equipment that we've got, which I'll touch on in the next slide. But essentially, we're looking at the unit which blends the hydrogen, which produces the hydrogen, and in the bottom, in the picture in the bottom middle, we're looking at the gas composition measurements. So making sure that we're meeting those GSMR regulations, making sure that we're providing the right quality of gas. So to give a quick overview of how the compound actually operates, we have natural gas coming into the compound at medium pressure, which is just above 1 bar. That goes into the hydrogen grid entry unit, which you can see labelled up. We then have hydrogen being produced on site by electrolysis, where you can see the electrolyzer is labelled. The hydrogen is then stored in the buffer tank. From the buffer tank, it goes into the grid entry unit, where it's blended using 4 static mixes with the natural gas. It then goes around the volume loop to make sure that the gas quality is of the correct composition, and is then released via the blended gas outlet into the network, where it's reduced in pressure, in low pressure, to feed the domestic and commercial users. And it's as simple as that. So in terms of where we are now, so as I mentioned before, we completed the safety case, we achieved the exemption. We installed the equipment on site, which you can see in the picture below. That's the compound. It's a small footprint, 20 by 20. And we have essentially been blending on site. Due to COVID, we have extended the trial until March 2021 to give us that optionality to gather some more evidence through these winter months. And in parallel to running this hydrogen demonstration, we're also doing some work on the boilers, which you can see in the picture in the bottom right. So we're running 8 boilers on long-term testing, where 4 are being run on natural gas and 4 on blended gas. And this will give us some data over the years, so we'll be able to extrapolate to around 10 to 15 years worth of data. Upon completion of the trial, we will then strip down the boilers and send them back to the manufacturers to analyze the components and see the impact from blended gas in comparison to natural gas. And we would ask the manufacturers, are you able to, before telling them, are you able to tell us which one were on blended gas and which ones were on natural gas? And it will be interesting to find out. So moving on from the Keele demonstration, I mentioned our first public trial, which we will be doing in the northeast of England. That will be in a village called Winlayton, located in Gateshead. where we will be looking to blend to around 670 properties in the Northern Gas Network's network using their Low Thornley site. So that's really building on the evidence that we've accumulated at Keele University and tackling those gaps that we weren't able to address. So we have been putting together the safety case, we've been installing and designing the equipment for the site, and hopefully next year we will commence the live trial at the northeast of England. Also looking forward, we will be doing some industrial trials, and the purpose of these is to essentially provide confidence that industrial users can take the blended gas, and this will help us facilitate a UK-wide rollout for blends. And that's looking at up to 20% hydrogen within the gas infrastructure. So we'll be investigating the implications on combustion, on control, on efficiency, on performance, looking at the emissions, and also the wider implications of having the presence of hydrogen on site. So we're doing 3 different trials. One will be done at Dunphy, who supply burners to many industrials in the UK. The trials will be done on a 1.2 megawatt furnace. We'll then be doing some work with Unilever at their chemical plant on a 7 megawatt steam boiler, which is a typical industrial steam boiler, and it will really allow us to tackle those evidence gaps. And finally, a large trial at Pilkington's, where a glass manufacturer on a 55 megawatt direct firing furnace, and we'll really be able to address those gaps going forward for the industrial applications to facilitate that rollout, and developing evidence on appliances which are 10,000 times the size of what we've been doing in terms of domestics. And finally, just to quickly touch on the overarching picture, which is a project called HyNet, which Caden is also working on, looking at a central production of hydrogen in the northwest via autothermal reformation. The orange pipeline you can see is where the carbon will be captured, and the black pipelines is the 100% hydrogen being fed out to the relevant users. And Hydrochlor really provides us that evidence base to be able to extract from that hydrogen source and blend into the network, and really unlocks rapid deployment of hydrogen in the gas network at scale. So yeah, that's essentially my presentation. I wanted to give a brief overview of the project, and hopefully that was worthwhile. I'll be happy to answer any questions.
Okay, thank you, Sikander. So we'll pause for questions. If you've got one, please type it into the questions box on the GoToWebinar portal. Well, I'll give you a moment on that. Let me remind you that this is one of a series of IChemE Global Awards webinars taking place throughout November. There's still plenty more still to come. They're all free to attend and open to all. If you'd like to find out more, please visit our website, icheme.org/global awards. Okay, we haven't got any questions, Sikander, so we'll move on. Thank you very much. It's now time to welcome our next speaker, representing Dow Consumer Solutions, Kaylin Frechelle.
Is my screen showing?
Yeah, we can see your screen and we can see you. Although your screen has just disappeared for a moment. So there we go. Perfect.
Great, thank you. Hi, everyone. My name is Kaylin Frechelle. I'm honored to be presenting on behalf of our team from Dow Consumer Solutions. Today, I'll tell you about the new process technology our team developed and implemented for the customization and packaging of liquid silicone rubber. I thought I'd start by describing what silicone rubbers are. They're a 2-part system which are blended and heat cured for rapid part production. They serve a diverse range of applications, from food contact and infant care to electrical insulation and automotive. While you're probably familiar with things like silicone watch bands and silicone bakeware, there are many things that we use on a regular basis that function better and longer because of silicone elastomers. For example, LSR gaskets are used in vehicles for protecting electrical components. This helps to extend their reliability and their lifetime. It's LSR's elasticity and strength that enables rollover airbags to maintain pressure. LSRs maintain their flexibility and durability in harsh environments when compared to organics. And this is why silicones are trusted to perform in the application, sometimes even up to decades. These trends for the LSR market explain some of the drivers behind our process technology development. For some applications, the cost of silicones can be prohibitive. So reducing the cost of production provides opportunities to reach more markets and new applications. The global silicone market is growing, which makes productivity both important for growth and sustainability. Our customers don't just expect reliable supply, but they're also moving to more customized formulations. They'd rather have a product tailored exactly to their application rather than a standard bulk product. For us, this means a flexible supply chain for supplying customized products is very important. Also, due to the sensitive applications that LSRs go into, tight quality control and monitoring are essential functions. Here's an overview of the process, the new finishing technology. So historically, LSRs used batch mixers paired with de-airing and packaging equipment. The team has modified the existing packaging equipment to design a semi-continuous process for customizing LSRs, and this eliminates the batch mixing step. As you can see in the diagram, a base material is customized with select additives or pigments right in line with the packaging process. The viscoelastic materials used in LSRs presented some challenges in the equipment design. The viscosities of our ingredients range from water thin all the way up to flowable solids. The team was able to resolve the design details for the process in order to maintain robust quality control over temperature ranges and viscosities that we would see in production. The process controls were also a critical piece in order to manage the various flows and to ensure tight quality control through real-time monitoring. The process is also a step forward in safety. Inherent risks were reduced by moving from large batch mixers to a smaller twin screw extruder. The reduction in the size of the headspace, as well as lower operating temperatures, eliminated any potential for flammable vapors contacting hot mixer parts, such as bearings. Additionally, the operators are no longer relying on lockouts to protect them from mixing tools during cleaning. Producing customized materials on batch mixers can require high labor costs, long changeover times, and larger amounts of waste. Due to the various additives and pigments that are used in LSRs, cross-contamination is a concern. Across the range of applications, there are compounds such as phenyl or fluoro compounds used in automotive applications that would be of great concern if they were to get into food contact or medical type products. So in batch mixers, these were dedicated to families of products in order to reduce any potential for cross-contamination and to reduce the frequency of mixer cleanouts. With this technology, we have the ability to dose and blend additives just before packaging, which eliminates the concerns about cross-contamination. This also provides higher flexibility in production and allows us to serve our customers with smaller volume, unique products for their specific application. And this is really, fast changeover is due to the self-wiping design of the extruder. We've gone from pigmented materials that are black to clear materials in a matter of minutes. The self-wiping design also eliminates any need for cleaning solvents in the system, reducing our overall waste footprint and also environmental impact. Overall, the new finishing technology addresses the conflicting needs of utilizing economy of scale to drive down the cost of production and also maintain the flexibility required for specialty small volume products. This technology has been deployed to 3 geographies and qualified with various customers. This required a talented global multifunctional team. You can see the members of the team here. The global implementation of this technology also allows us to increase the sustainability of our supply chain through localized supply. In summary, our new process technology for customization of LSRs increases our efficiency. We've seen greater than 30% increase in productivity. We've seen an improvement in quality control in our CPKs. For those of you who are familiar, we've made a step change improvement in safety and allowed for future growth through reductions in waste, capital, and the footprint of the actual equipment. With that, I want to thank you all for your attention, and I'd be happy to take any questions.
Thank you, Kaylin. So once again, it's time for questions. So if you have a question, please type it in on the GoToWebinar portal. We'll just pause for a moment on that. Don't forget, the winner of this award automatically qualifies as a finalist for our top prize, the Outstanding Achievement in Chemical and Process Engineering Award. You can join us for that webinar later this month. Once again, visit IChemE.org/global awards for details. Okay, I don't think we have any questions, Kaylin, so thank you very much. We're going to move on. Next up, representing the joint entry from Dow Europe and H&S Anlagen Technik, it's Lucy Puccelli.
Hello, everybody. Can you see my screen and myself?
Yes, we can.
Perfect. Hello, so my name is Lucy Puccelli and I'm the Business Sustainability Leader for the Dow Polyurethane business. Today, we would like to tell you more about the Dow Renuva Mattress Recycling Program and how we are working as the industry to achieve circularity for polyurethane. I will be mentioning 3 key points about the Renuva program: how it is addressing the current waste issue, the fact that with Renuva, we can now demonstrate that polyurethanes can be recycled, and emphasize the importance of the collaboration. But now I would like all of you to think about last time you bought a new mattress. And more than that, think about what have you done with the old one. Because today in Europe only, more than 30 million mattresses are being thrown away every year. If we were to stack them up, the pile of mattresses would be 678 times higher than the Mount Everest. Today, these mattresses are mainly not recycled. They are ending up in landfill or, in better case, incineration. We are literally burning the value we can have if we can reuse or recycle the mattresses. And this is the key problem Renova wants to address, the waste issue, and the fact that we have produced those materials, in our case, polyurethane for mattresses, which provided comfort for approximately 10 years when you were using them. But now we have to move forward and look what's happening with those materials at the end of their life. Our Renova is a circular economy roadmap. It is really the way how we want to collaborate with the value chain, enable end-of-life polyurethane product recycling. Because we are building up the whole new recycling value chain, we can have much larger sustainability impact. We can leverage the expertise. Of course, along the road, there will be new jobs being created, and it will encourage further innovations and collaboration. Second, Renova really is a demonstration. It's not a concept, it's not the idea, it's something which is already happening. First plant which can recycle post-consumer polyurethane waste, which is coming from the end-of-life mattresses, is already underway. The product, and it's expected that the product will already be started to produce at the first half of 2021. The process is using chemical recycling or solvolysis, which is then converting the solid polyurethane waste back to raw material it was used to create it, polyol. The biggest advantage of this process and the chemical recycling itself, that it breaks down the foam on the molecular level. We don't have to do additional cleaning of the waste material. Also, at this current process we are implementing in France, there is no need for a pre-treatment of the waste. That means we don't have to separate different types of foams. And most importantly, this has an immediate impact on that waste issue. At capacity, the plant in France will be able to recycle 200,000 mattresses per year, creating raw materials which can be used as a high-quality materials to produce new polyurethane. We can achieve up to 50 or up to 30% replacement levels while having comparable properties in both applications. And last but not least, I really want to spend time and looking at the collaboration we are enabling and the ecosystem we are building. The recycling process can only start if we have access to waste as we have access to feedstock. And here we have in France a partner in Ecomobilier, who is the unique extended producer responsibility scheme in Europe, managing both furniture and mattresses. They will be provided the waste foam, waste polyurethane foam for mattresses for the process. We have also the great collaboration in H&S Anlagentechnik, who is the German engineering company specialized in the polyurethane industry. They are providing the process know-how and the turnkey installation for the chemical process, which is then operated by our external manufacturing partner, Orion Chemicals Orgafoam. They will operate the unit to convert the waste solid polyurethane foam back to liquid polyol. We have Dow, who will be supplying the raw materials and ensuring that the process and also the resulting polyol is compliant to all the regulations. And last but not least, we also have already the end user in the circle since the beginning, because it's important that the materials we are creating through recycling have a use and can be used, and the new materials can be created out of them. In that case, by the group. To summarize, we really think the Renova program and the Renova polyols are helping both society and the environment. We are addressing the waste issue we currently face. There will be no need for landfill and incineration of the polyurethane mattresses. For the industry, this is a demonstration. Polyurethanes are recyclable. They can be recycled. What's needed is the right infrastructure to do it. And this process is also reducing overall carbon emission. And last but not least, collaboration is critical to enable it. If we do, we can then provide to all of us more sustainable choice next time you go and buy a new mattress. Thank you for your attention, and I'm very happy to take your questions.
Okay, thank you very much, Lucy. So once again, we'll pause for questions. If you have a question, please type it into the questions box now. While we give you a moment on that, now is a good time to thank our volunteer judging panel, led by our head judge, Keith Batchelor. The judges work tirelessly to review and score every entry we receive. You can find out more about the judges on the IChemE Global Awards web pages. Okay, we don't appear to have any questions, so thank you, Lucy. We will move on. It's now time for our next finalist. Representing Dow Inc., please welcome George Neubauer.
Can anyone hear me?
Yes, we can hear you.
Okay, now I've got some odd information here on my screen, but so how do I share things here?
We can see your screen, so if you bring up the PowerPoint window.
Yeah, there you go. This is the right one, isn't it? Okay, let me just go to presentation mode. So I'm not seeing myself, but that's probably good. Yeah, so I'm good day everyone again. So I'm Jörg Neubauer. I'm and on behalf of our team at Dow Construction Chemicals, I'm going to present our entry to the IChemE Awards. This is high efficiency ultra high viscous Valosyl M12001 cellulose ether. That's a fairly long title here, but to begin with, let me introduce some things and some news about cellulose ethers and their use in construction materials. Water-soluble cellulose ethers are used as high-performance additives in dry mix mortars, and at a low dosage, that's about 0.5%, typically less, they significantly improve the water retaining capability of a mortar. And water retention is critical for the thinly applied mortars and on absorbing substrates, because water is required for proper hydration and final strength development of cementitious or gypsum-based materials. Added to cement-based tile adhesives, for instance, cellulose ethers improve workability, enable tiling efficiency, and guarantee a long-lasting floor or wall covering, as shown here on our picture on the right. However, the amount of cellulose ether added has an impact on formulation cost. Therefore, the dry mix producers are seeking lower cost options, and certainly without compromising quality or performance. Water retention of conventional cellulose ethers depends on the molecular mass of that product, and that again depends on the molecular mass of cellulose that's used in the production process to obtain the material. And the molecular mass of cellulose is defined by nature. So cellulose obtained from cotton linters, that's one source, others certainly wood, has the highest molecular mass. Consequently, cellulose ethers produced with this material provide the highest level of water retention. And these cellulose ethers also have the highest aqueous viscosity, which our industry uses as a measure for molecular mass and also for, consequently, water retention efficiency. And if you look at our graph, the schema on the right, there's the N indicates the number of repeat units in cellulose, and while N is highest for cotton linters, in today's process, this N doesn't really change. So there's no way to make N any larger after the chemical reaction. So basically nature limits the molecular mass as well as the water retaining capabilities of any new cellulose ether development. So that certainly is not great. So what did Dow do? And we developed a new process for cellulose ether production that involves chain branching. The new technology, for the first time, can overcome the restrictions between cellulose raw material and cellulose ethers obtained from it. Our new process provides very high molecular mass cellulose ethers through branching, and that results in unprecedented levels of water retention and product efficiency. Let's have a look at the next slide. The chart on the left schematically depicts how cellulose ethers are produced. You've got ground cellulose here, bottom top left, and then this is reacted with sodium hydroxide. That's the alkalization. Then we add ethylene oxide and methyl chloride. That's the esterification step. Then there's purification, and the material is finally dry milled, and we end up with the water-soluble cellulose ether. And our new process includes one additional step that's highlighted in red. That's the chain branching agent is added to produce chain branched cellulose ether by the cell M12001. This is a pressurized high temperature cellulose ether production process. It's a three-phase heterogeneous high solids reaction, and unfortunately, or probably luckily, all chemical and engineering parameters have been optimized for high yield esterification. But in the end, no one really anticipated the addition of a chain branching reagent at the time. So the engineering challenge was there, and it was to introduce a branching agent to an already optimized process. At the same time, preventing gelation during esterification through homogeneous distribution of our branching agent, because finally we needed our cellulose ethers, also the branched ones, to remain fully water soluble. For process development, that's shown here on the next slide. For process development, and that you've got an idea about the different scales here, the lab scale, the pilot plant scale, and the plant scale, by the way. For process development, we started on lab scale, continued to pilot plant, and scaled finally up in production. And each of these steps had their specific issues that required to be overcome. So on lab scale, we first confirmed that our concept works, and we figured out key process parameters. And with lab scale material, we developed new characterization methods for these branched cellulose ethers that didn't exist beforehand. For pilot plant scale, we had to adjust mixing and dosage regimes and ensure that the activity of this exothermic reaction was fully under control. For this, we confirmed sufficient heat of reaction transfer with a small volume cooling mantle ratio of the pilot plant reactor that we had at the time. And in the pilot plant itself, we evaluated process concepts and finally confirmed the process parameter settings, and at the same time were able to produce material for evaluation at our customers that we collaborated with. And when scaling up commercially, we installed equipment to add the branching agent where and when exactly it was needed in the process. We were running multi-batch campaigns and successfully integrated the additional dosage step into the existing esterification process. And finally, upon launch of branch cell M12001, we had managed that our run rate as well as the batch size remained on the optimized pre-branching levels. That was a big success. And let's have a quick benchmark here at the cell M12001 and compare it to some regular high viscous cellulose ether from the market. The graph on the right tells it all basically. It shows that on the right the gray the standard product and the red one is the cell 12001. And if you look at it, water retention of a regular cellulose ether at some standard dosage is 96%. That's fairly good. But as dosage is reduced by 25%, we end up with a significant drop to only 89.5%. That's a significant difference. And for our new branched cell 121, water retention is at the reduced dosage as much higher. It's 95%, and that's essentially comparable to the value of the regular cellulose ether, but at 25% dosage reduction. So these results that they confirm the unprecedented water retention capability of branched cell 12001 and enables producers of cement-based tile adhesives to save up to 25% dosage of cellulose ether compared to any regular high viscous cellulose ether out there, without compromising workability and having same application performance. So wrapping up, let me just summarize quickly the key learnings here from the development of the ultra-high viscosity cellulose ether. As performance additives, just mentioned, the cellulose ethers improve water retention. And in 2020, in earlier 2020, Dow launched high-efficiency ultra-high viscous valid cell M12001, which is the first commercial cellulose ether ever based on IP-protected chain branching technology. And due to this high efficiency, water producers can reduce cellulose ether dosage by up to 25%. Formulation cost improvements support the adoption of high quality and more sustainable dry mix mortars also in developing markets. And last but not least, Dow will use the patented chain branching production process as a new technology platform for the development of highly efficient cellulose ethers for also other dry mix application segments. That's been my story here. Thanks for your attention, and I'm certainly happy to take any questions now.
Okay, thank you very much. So once again, we'll pause for just a moment for questions. Then if you have a question, please type it into the questions box. Okay, we have several questions coming in. So first one, is cellulose used the same as organic biomass?
Can you please repeat the question? So that's been
is cellulose used the same as organic biomass?
Cellulose is a sort of refined and upgraded organic biomass. So if you basically take a tree, you don't necessarily can start producing cellulose ethers based on it. So you really have to turn the wood or the biomass into cellulose by doing some cleaning and purification processes. The cellulose is the same that's used for paper production, for instance, or for cartons or material like that.
Okay, and the follow-up question is, have you got any data on the carbon footprint of the cellulose?
There is data for carbon footprint on cellulose because that's not what we produce, but what we use as a raw material. We do not have data publicly available for the cellulose ethers that Dow produce.
Okay, and a third question, has any preliminary work been undertaken to convert cellulose to 2G ethanol?
This I don't know, so that is definitely not our line of business and not my expertise. I'm sorry about this.
Okay, no problem. Well, look, thank you very much. We have time for just one more question, I think. Let me just get this one. How does the production cost compare for Wallacell with the standard cellulose ether?
That certainly is an information I really can't tell. That's an information that Dow prefer keeping to themselves. What I can say is it's a product that we produce and sell, so we are not losing money doing this. Put it like this.
Okay, I understand. Well, look, thank you very much. It's time to move on. So please welcome our next presenter now from Dow Silicons Belgium. It's Francois de Boyle.
All right. So show my screen. How do I share that? How do I share the right screen? That's a question. Do you see the proper screen?
Yeah. We can see your PowerPoint, but if you just switch the display settings so we can see the presentation view.
All right.
On the top left, there's a drop down which says display.
Yeah. Screen monitor 2. There we go. All right.
Perfect.
Seems to be the right one. Okay. And I don't know if you see the camera on. Yes or no? Share my webcam. Okay.
Now we do.
Okay, let's get started. Oh, yeah. What's going on? Sorry. I'm struggling with the screen. How do I remove my face from this? Up. All right, so let's get started. So again, hi everyone. Good afternoon. Good morning. Once again, a DAO presentation here. So actually, I'm sorry, but there is a lot of windows popping up, which is really annoying.
Hi, Francois. It's Cassandra
here.
here.
There we go. Yeah, there we go. So actually, yeah, it's a great pleasure and like for the others, honor for me today to present our work of a great team of people actually who worked hard in the development and commercialization of a family of optical silicon rubber used in a wide variety of LED lighting fixtures and design application. And actually at this stage, I can already thank my colleague Kaylin to have introduced technology of LSR, so liquid silicon rubber, because I mean this project is really about a particular family of liquid silicon rubber. So as you may see on the world map here, since 2012 now, our team, enriched by an extreme diversity of people, issued from different generations, and some of these persons on the screen have retired already, from various origin and with quite diverse material science expertise. This is really the story of this team that I would like to share with you today in the few next minutes. So first aspect, did you know that since the inventions of this incandescent bulb by Swan and Edison, the end of the 19th century, the modern LED invented by Nakamura have really started to revolutionize the world of lighting, and so that since 2000s basically. So I'm a member actually of a technical support and development team based in Dow Silicon, Belgium. And I hope that I can enlighten you today and bring your attention to the benefits of this moldable optical silicone and what they have brought already to a wide series of LED lighting application and beyond. You can see on the right-hand side of this picture the few four actually of example of successes with customer in the lighting industry partners that, for instance, Philips have developed a UV water disinfection system based on optical silicone window. VS Lighting have developed street lighting for roadway illuminations with these silicon optics. A famous example is with Hella, who developed adaptive driving beam LED headlamps for Daimler initially. And the fourth example here is with Gajon for a unique design of optical collimator used in retail lighting. Actually, the key drivers of the spread of the use of LED lighting technology in most lighting applications today are the access of high power LEDs and the need of high efficiency in light extraction and control. The second important aspect is the opportunity to reduce maintenance and ensure long-lasting performance of the lighting fixtures and module. Third aspect is the opportunity to combine multiple features at the secondary optic level, like in the adaptive driving beam or in outdoor lighting fixtures. And last but not least, the necessity to reduce our carbon footprint and energy consumption, which actually the adoption of LED has made possible and significant, with saving up to 70% in daytime and 50% in nighttime use of lights. So now, well, let's see in a high level what optics component made of silicone is, instead of traditional thermoplastics or glass material, can effectively bring to the LED lighting fixture designers and engineers. So on this illustration, a couple of pictures that shows how under the Dow brand SILASTIC, that was well established already at the time of the former days of Dow Corning, for the promotion of our liquid silicone rubber. These moldable optical silicone offering readily optically clear, like glass clear or white reflecting, and at the same time tough material when molded into a given shape, with particularly excellent environmental stability for a wide range of LED applications. You see here on the screen an example of TIR lenses with highly polished mirror-like surfaces to enable total internal reflection of the light and perfect control of the light beam angle projected from the light sources. A light guide with the toughness and flexibility characteristics of silicone rubber. The third picture here in the middle shows a linear optic design with microstructures that enable to control light scattering and diffraction out of the light engine aligned behind. You can even go to holographic type of effects obtained by a submicron deep grooves that has been let's say molded onto the surface of the optics part, and that enable to control light diffraction and projects such as like the pictures show rainbow spikes surrounding the center white light beam. And as I mentioned, we also have highly white reflecting, up to 99% reflectance, moldable optical silicone that can be used to design reflectors with negative draft angle to achieve a wider beam angle than conventional reflector based on specular materials. Let's move to the next slide here. So right now, a true example I would like to really spend a bit more time is of industry projects, partnership. And as you have already heard, partnering is really key in most of our industries. Is this example of adaptive driving beam that HELA had designed for Daimler cars back in the 2015 already. And if I bring to your mind that dark or low lighting condition on roads increases likelihood of collision up to and actually cause 50% or more of driver fatalities and up to 70% of pedestrian deaths. You can readily understand the importance and the value of this new LED matrix adaptive driving beam car headlamp system that was designed by HELA and that we further, let's say, help to make to become a reality. And today, I mean, up to 30 or more car models are equipped with this technology of LED lighting. And the true collaboration between industrial partners like Henkel, ACH Effner, and many others to optimize the injection molding processing of optical LSR was really key for the success of this technology for cars OEM. Moving further. Yeah, moving further out of, let's say, automotive lighting application, there is a wide variety of other lighting application that are shown on these pictures on the screen using this optical LSR. For instance, for retail, high-end quality retail lighting, stadium lighting, football and other sort of stadium area, architectural, so large size building, architectural lighting outdoor, and street lighting application. These are areas where the value of silicone has been, let's say, recognized for first outstanding resistance against high lumen fluxes and heat generated by these high power LED or chips on board sources. The intrinsic resistance of silicone against outdoor UV, the benefits to bring highest ingress and impact protection. I mean, silicone with these rubbery characters can readily improve impact resistance compared to rigid thermoplastics and glass. And then finally, the naturally best flame retardancy performance of silicone rubber, I mean, enable these case studies, I mean, really effectively. Many examples of these case studies, by the way, can be found on our Dow.com pages, searching for lighting and optics pages in particular. And yeah, coming back now on the teams and the team aspects of the team spirit, I would say, in the dynamic. There is now almost 9 full years that I'm personally enjoying working in that field of application for Dow silicones. And well, we are bringing the science of silicone, the chemistry of the material, the physics of optics, and the engineering of injection molding processes to our customers. And you may see on these pictures the smile of our faces are real, to be honest, when we participate to multiple exhibitions and conferences. And it's really a passion that we like to share and pursue, enjoying working and helping our customer in the field. And with that, I really would like to also thank organizer of IChemE Awards, and I would say time to time it's rewarding to be recognized as a finalist in this kind of things. So great thanks for your attention, and I'm happy to take any further questions.
Okay, thank you, Francois. So it's Q&A time. So if you do have a question, please type it into the questions box, and we'll just pause for a moment to give you a chance to do that. Okay, we have some questions coming in. So the first one, is it more cost effective to use moldable optical silicon or thermoplastics in production of LED equipment?
All right, okay, yeah, that's a good point, and a very frequent question that actually our customers and partners are asking. Let's say like this, liquid silicone rubber are thermosets. You start from 2 liquids, A and B, you mix together at room temperature, and then you have actually a relatively low viscosity. In case of optical LSR, the viscosity is really low, lower than standard LSR that Kaylin was referring to earlier. And so on that perspective, the processing with a silicone press can be more effective, more cost effective than with a thermoplastic melt that you need to heat, and then the high viscosity melt need to flow into the cavity, the optical cavity in which you mold the parts. And already at that stage, the size of the press to produce LSR molded part compared to thermoplastic molded part, the size of the press will be significantly different. So you can use lower tonnage presses for silicone than for thermoplastics. Now, on the other hand, with silicone, we bring, in certain cases, definitely proven benefit in terms of performance, UV resistance and long-lasting performance. which has a premium, let's say. The raw material cost is higher, definitely, for a silicone, optical silicone rubber than for thermoplastics, that's no doubt. But the overall balance at the end make possible to optimize cost per part in a reasonable way to be competitive, or a bit higher certainly on prices at the end than thermoplastics, but competitive for the benefit it bring into the application targeted.
Okay, thank you. Next question. What is the end of life solution for the products made from silicon after use? Is it easy to recycle, or is it landfilled?
All right, yeah, good question as well. Again, these silicone rubbers are thermosets, so you cannot just recover the part and melt them again, because it will not melt. Actually, it will burn. It will transform into quartz and silica. Now, having said that, there are projects and opportunities to use cured silicone rubber or sealant or adhesive made of the silicone curing chemistry. You can use these components, eventually grind them into, let's say, grinded silicone rubber, gross particles, I would say, and eventually disperse them into secondary, let's say, uses, not anymore optical in this case, but secondary use, like a rubbery sort of filler into bitumus, into different application that will benefit to be added with this material. So the recycling, I mean, is different than the thermoplastic, definitely, and work needs to be done and continue to be done to that respect.
Okay, thank you very much. It's time to move on. So thank you for that presentation. And our next speaker represents the joint entry by Florence Energy, Mintra Energy, and MK Aromatics. It's Oshim Merchant.
Press the play button. Stop. Disappeared. Good afternoon, everyone. Can you see my screen?
Yes, we can.
All right. So I'll start. All right. Very good afternoon. And can you see me? Do you need to see me, or can I just go ahead?
We can't see you. We don't need to see you. It'd be nice to see you, but it's not an essential.
1 second. So my mouse. There we go. Yes, there we go. Getting a hang of it. Right. So all good. You can see me and the presentation, yeah?
Yes, we can. Yes.
Great. A very good afternoon to distinguished attendees, colleagues, and my dear friends. First, my deepest thanks for recognizing my company as a finalist for this year's prestigious IChemE Industry Project Awards. To have been shortlisted among the titans of the industry and global leaders such as Dow, Johnson Matthey, and Saudi Aramco has been both humbling and exciting. Thank you. To have come this far, it has been made possible due to the extensive support we have received from the University of Adelaide, South Australia, Chulalongkorn University, Thailand, Swedish Institute of Management, my dedicated staff, and every individual who have believed in me and in the vision of successfully implementing plastic to fuel business models to tackle the twin challenges of environmental conservation and clean energy. My journey started 12 years ago when my ideas were seen to be overly optimistic and wildly improbable. From suggesting the production of terephthalic acid using supercritical carbon dioxide, or using resin ion exchange columns to extract traces of gold found in tailings, you could say that my career has always resided in uncharted territory. This has been driven by my hope, optimism, and desire to be a solution contributor and preferred partner in shaping a better future and a more resilient future. We live in a competitive world, and in this competitive world, survival sometimes forces us as companies or individuals to take shortcuts to survive. Plastic pollution, as we see it today, is a result of those shortcuts that were in effect for the most part of the last 2 decades. Prior to COVID, plastics were demonized as one of the greatest threats to humanity because little efforts were directed towards their safe and sustainable disposal. Yet, post-pandemic, the very same plastics are now seen as the saviors of humanity. It is an undeniable fact that plastics have contributed to world peace since World War II by delivering to the people accessibility and affordability of basic necessities. The invention of plastics is mankind's greatest asset. What is required of us at this point in history today is to expand on our knowledge, our learnings, and direct investments to bridge the gap to economically and sustainably treat post-consumer mixed plastic wastes. Today, I would like to take this opportunity to reassert that post-consumer plastic wastes are an exclusive alternative feedstock and is the bedrock and foundation for prosperity over the next 20 years. There is tremendous value and upside potential in the production of polymer oil based on its unique inherent characteristics. End-to-life chemical recycling solutions are a proven system to unlocking economic value and creating quality full-time jobs. Most importantly, it results in the socio-economic upliftment of the poorest of the poor sections of society today that earn a living from the waste industry. And if you have been to a landfill, it is a sight that is truly below the dignity of human labor and is unacceptable in the 21st century. My company has distinguished itself on 3 key parameters. The first is we design, build, and operate world-class plastic to fuel, waste plastic to petroleum facilities, where our focus is on plant operations and product delivery. We do not sell our plant and machinery. The second point is we co-invest and build strategic partnerships with like-minded companies and would like to thank Unilever, Britannia, Kothari Petrochemicals, Pepsi, and all our suppliers and customers for having supported us to reach where we are today. And most importantly, product delivery defines us. With a track record of having produced over 21 million liters of polymer oil from over 28,000 tons of waste, it is important to recognize the most important aspect that actually drive the creation of an industry. It is the will, the grit, and the experience of the leadership team. At the end of the day, technology is only limited until the factory is able to run, manage, and produce a product that brings value to the market. And in a world blinded by automation, machine learning, and artificial intelligence, I would like to reassert that innovation, creativity, and grit are human values that no level of automation can ever replace. On behalf of my consortium with established commercially operational successful plants, we firmly believe that the plastic to fuel industry is at a tipping point and poised for exponential growth. In an industry where there has been too much smoke without fire, it has not been an easy journey. And against all odds, we have grown from strength to strength with extensive knowledge in pre-processing, post-processing, catalyst development to provide a range of tailored niche products to our customers today. We are a young team, hands-on and dedicated with an enormous appetite to grow and to be of service in tackling both the menace of plastic waste and providing clean energy. We are not here to compete. Instead, we are here to collaborate and create wealth, because that is precisely what industries do. Chemical engineers are the inventors and magicians of this world, because at the heart of what we do is merely convert one material from one form to another efficiently within nature's guiding framework of undisputable mass and energy balances. And that is exactly what we do with depolymerization technology, or molecular recycling as commonly referred, of post-consumer mixed plastic wastes. No sorting, washing, or drying is required, and with our scalable modular polymer energy systems, we melt, vaporize, and condense post-consumer plastic waste to high-value hydrocarbon derivatives with zero air and water emissions. Please feel free to reach out if we can be of service, and it would be an honor to extend an invitation to the distinguished companies present here to visit our factories. Together, we can rapidly build economies of scale in this industry and advance human security by successfully tackling climate change profitably. Thank you very much.
Thank you very much. So once again, we will pause for questions. If you have a question, please type it into the questions box. Whilst I give you a moment on that, if you've been suitably inspired to submit your own entry to next year's IChemE Global Awards, keep an eye on our website for entry information. We typically open for entries at the start of March each year. So head over to icheme.org/global awards after the webinar to find out more. Okay, we don't have any questions for this one, so thank you very much, Ocean. We'll move on. Next up is Johnson Matthey. Please welcome Simon Sputnik.
Thank you very much, and hello to everyone. My name is Simon Smrtnik, and I work as an associate specialist in formaldehyde technology in JM in Sweden. And this presentation, I'm going to present to you an innovation that we successfully made to our formaldehyde production plant, increasing pressure and productivity. First, something about our company JM. Our vision is for a world that's cleaner and healthier today and for future generations. We work with our customers and partners across markets, from pharmaceuticals and medical to automotive, industry and chemical production. And we use this science we have to tackle three global challenges as we see it. And that's the need for clean air, conservation of the planet's resources, and the requirement of affordable health care for each and every one of us. And this enhanced life for millions and millions of people globally each day. And we do this by invest resources in research and development and having cutting-edge science. We have 1,600 people employed in research and development. We strive for partnerships with our customers, building long-lasting relationships, and those are built on trust and mutual understanding. So we are understanding their problems that we solve by our profound knowledge and experience. We develop new solutions by our detailed modeling and understanding of material and production processes. And this enables us to develop new materials and design new processes at a commercial scale. And of course, this brings value to our customers by more efficient and safe production. And that will also lower the investment costs and reduce the environmental impact. Formaldehyde has a long-lasting history, and it ranged back to the 19th century, where we had the Russian and German scientists Butlerov and Hoffman that were performing experiments on a laboratory scale. They were oxidizing methanol to formaldehyde. This was then further developed through the years, and in 1959 the first commercial scale plant was set up and started in Sweden. where we had and are still using an iron molybdenum catalyst that is used in a tubular reactor in a gas phase reaction taking place. This formaldehyde, which we have in the gas phase, is then further absorbed in a liquid, water, and is the product which is then called formalin. And the installed capacity of producing formalin is about 80 million tons, and it's used about 70% in worldwide of this installed capacity. And the market is divided into two segments, basically. It's the wood segment and it's the chemical segment, and they are equally sized. In the wood, we the customers use formalin to produce resins that are then further used to produce boards, fiberboards, laminates. And you see in the right hand pictures of example of products. The chemicals is a segment that is growing, and we see new chemicals like MEG and PBAT that will require very large plants, formaldehyde plants, due to higher demand. And product in the chemical is like POM, which is used for hard plastics like the cog wheels that you see here in the picture. It's used to soft materials such as spandex clothes or rubber materials, like we heard earlier here in the presentations of the mattresses of the polyurethane. But it's also used for coating in agriculture industry and, for example, in lube oil. So we had a wide range of products where the basic chemical is this small, tiny formaldehyde molecule, which you see far down to the left. So it's like I usually say, the minimum Lego piece, which is very easy to use and to build up bigger molecules, polymers. JM is leading in the formaldehyde oxide process, and this has been achieved by continuously working with innovation, where we have involved all disciplines from plant engineers, catalyst engineers, to sales and technical support. And as you can see in the chart here, the red line, and on the right-hand axis, we have increased the production per ton from 8 to 32 kilograms formalin production per tube and day. And that is an increase of 400%, and that's a really, really big achievement over the years. And this has then been done by, for instance, increasing the gas flow in the process. We introduced recirculation to reduce the oxygen concentration in the gas phase, because that enabled to increase the methanol concentration that is used to oxidize into formaldehyde. So if the oxygen was decreased, we were avoiding to be in the flammable region between the oxygen and the methanol. But of course, we have also worked very hard and dedicated to improve and adapt the catalyst, because it needs to handle a more increased methanol concentration, and with that increased activity. So we need a stronger catalyst to avoid that it's degrading or falling apart when it's exerted to higher production. So as I have said earlier, we developed our plant and catalyst for higher production by increasing the system pressure from 0.5 to 1 bar gauge, and that increased the capacity of the plant significantly. And in the same time, of course, it's also lowered the investment cost for our customers. It has also the benefit of decreasing the economics of operating the plant, as the power input was reduced if you calculate it as power input per produced ton of product. And we have kept our high performance with this plant, although that we are increasing the production so dramatically. And we had also, of course, to improve the reactor cooling due to the higher heat load exerted in the reactor, since the reaction between methanol and oxygen is an exothermic reaction. And we also had to redesign our incineration process, where we are oxidizing the effluent carbon hydrates and carbon monoxide to carbon dioxide and water to make it more in a smaller scale, at a smaller price. And we used our latest knowledge of safety standards and listened to our customer needs. So that has been the key the whole time, that we have been working so close to our customers and implementing their input into our development. So this is a remarkable effort with this new plant that was made, and it was made possible by close cooperation between the disciplines, as I mentioned earlier. The plant engineers, the catalyst engineers, all taking input from sales and technical support. And it was made only in 4 years, from the first kickoff meeting that was held in April 2016 until October 2019. And in between, the catalyst was developed for higher pressure, and it was tested in another customer plant at more harsh conditions. And as it was shown to be good, the results were very promising. We were able to sell our first commercial license in June 2018. And our engineers worked really, really strong and hard. And already in October last year, we had this first high pressure technology plant started. And that is something that we are really, really proud about and would like to share with you. Thank you for listening. So,
okay, thank you very much.
So anyone has any questions?
Yeah, so once again then, if you do have a question, please type it into the questions box, and we'll just pause for a moment to give you a chance to do that. Don't forget, we are live tweeting throughout all of our 2020 IChemE Global Awards webinars, and you can also get involved using the hashtag IChemE Awards. So we have a question. What was the capacity of the first commercial high pressure tech plant?
The capacity of our first plant is 400 metric tons per day. Oh, and then we calculate it as the standard is to calculate it in what we call 37 weight percent of formalin in liquid solution.
Okay. Our next question is, do JM produce this themselves, or do they sell technology?
We sell the technology, so we license the technology to our customers, but we also are able to help them in the construction phase, because we have profound experience since decades. There is a variety of constellations of how it is made, but sometimes, or quite often, we also source the equipment to the customers, and then we have a construction company that is a third party who is then assembling the plant, and then we have our team that goes to the plant and has performed commissioning work to check everything out before the plant is started.
Thank you. Our next question, is 400 tons per day the minimum viable capacity, or can it be done at a scale from 50 tons per day?
Yeah, it's a wide range of production capacity of our plants, so it can be reduced. I don't have the exact number here, but it's like maybe down to 30% or something like that from those 400. So that would be around 100, 120 metric ton. But we then have other plant sizes. So you can go down for we can offer a smaller plant, and that can then go down in capacity if that's the need of the customer, or we can offer even larger plants to the customer, and then also having this enhancement of increasing the pressure more, increasing the density, and then they can produce, of course, more from the equipment.
Okay, well, thank you for your presentation and thank you for answering those questions, Simon. It's time to move on.
Thank you
we
very
have
much.
reached our final presentation of the day, representing Saudi Aramco. It's Mubarak Al Rashid. Okay, we can see your screen, we just can't hear you yet, so you will need to unmute your microphone.
Okay, can you hear me now?
That's much better, thank you.
Okay, no problem. Good afternoon, ladies and gentlemen. My name is Haider Bashir, and I'm one of the process engineers at Upcake Plants here in Saudi Aramco. I'll be sharing with you some of the details of how we restored our facility and global oil production following the terrorist attacks on September 14th, 2019. Before I start, I'll share a little bit about the facility that is Upcake Plants. The facility is located in the eastern province of Saudi Arabia, and it processes up to 6 million barrels per day of crude oil, which amounts to roughly 5% of global oil production. And this in turn makes it the largest oil processing facility in the world. The facility is an old facility. It has a long history, starting soon after the discovery of oil in the Upcake area, which was in around 1940. Over the decades since, the facility has grown organically and includes degassing and stabilization of 3 different grades of crude oil, NGL production, as well as steam and power generation, which is used in the facility and as well as exported to other customers. As I'm sure many of you will be aware, in the early hours of September 14th, 2019, there was a fierce and unprecedented attack on the facility, primarily by aerial drones, which impacted over 15 critical pieces of equipment. And you can see some of the damage on the pictures you see now. This created a number of raging fires across the whole facility and shut down 5% of global oil production. Before I proceed further, I would like to just play a brief clip, which will give you kind of a taste of really the intensity and ferocity of the event that took place. Based on the really significant devastation caused, a lot of industry commentators, including Bloomberg, expected months of disruption. But the reality was that we managed to restore that production capability in less than 2 weeks. And we sustained it. And that was essentially by 3 separate teams of engineers working around the clock to carry out the hard task of figuring out how we could supply on-spec products through whatever remained of the crippled infrastructure of the facility. The rapid restoration was carried out by prioritizing immediate recovery solutions, which was just to get some production commenced. And this was followed by efforts to ensure that that recovery was sustained, and also so that we could ensure that the full portfolio of products and crude grades that we supply could be delivered to our customers. Now, in terms of the recovery, 10 stabilization columns were impacted directly by the attack, including all the associated utilities, as well as the adjacent pipe racks. So over 25 bespoke procedures were developed to safely isolate, repair, segregate, and start up each equipment. And this was following rigorous hydraulic analysis and relief adequacy checks for the system that was available for use. Furthermore, 9 of the 11 degassing tanks on site were directly impacted too. So to commence maximized production, several of the tanks were patch repaired, which entailed a detailed risk assessment to operate the tanks with derated design conditions and the introduction of additional layers of protection. Furthermore, we created a new operating regime with upstream facilities to try to maximize the degassing upstream and hence allow higher liquid rates to be processed through the facility. And this kind of global optimization allowed us to process 20% additional crude oil, while ensuring we maintain the balance between degassing upstream and ensuring that no flaring took place up in the upstream facilities. Another area of the facility which was directly impacted was the wastewater treatment area. And again, in order to ensure that the treated water quality was maintained prior to disposal, we optimized the residence time by utilizing alternative storage volume following risk assessments to make sure that was safe to do so. The damaged columns I mentioned earlier were repaired rather than replaced. They were removed to local fabrication shops in order to both reduce wastage as well as improve the time for repairing. One of the kind of core values throughout the restoration was to kind of embed sustainability, safety, and enhanced resilience into the design. And the column repairs were utilized to upgrade the metallurgy of internals, install new feed distributors for increased tray active area utilization, installation of vapor balancing lines for improved thermosiphon stability, as well as enhanced intrinsic process safety by making sure the columns were suitably designed for vacuum conditions. All of these enhancements yielded an overall reduction in facility energy intensity of around 0.3%. Of course, I mean, you can see the scale of the task was large. So a total of 58 different design packages were developed during this process, and they were reviewed and tracked through an optimized MOC process to try to achieve a rapid restoration. And of course, this included multiple process risk assessments. This task was carried out by over 20 process engineers working around the clock in the 3 teams I mentioned earlier. The fruit of all these endeavors was the restoration of oil production of up to 6 million barrels per day in an accelerated but sustainable manner, defying expectations and providing stability to oil markets as well as wider society, which is of course dependent on the availability of hydrocarbon fuels. And perhaps the real success story here was that all of this was achieved without any process safety incidents, any loss of primary containment, fires, or environmental impact. Furthermore, we use this kind of adverse conditions as an opportunity to improve facility resilience, performance, and flexibility. In addition to the performance improvements I mentioned earlier, we also increased the firewater availability through reuse of other water streams that were available in the area. And last but not least, an alternative processing configuration was developed. And this was to utilize other columns and control valves in the facility to stabilize up to 25% of plant capacity as an automated backup in case of any similar type of emergency. As you can see, this had a significant impact. The oil markets reacted to this rapid restoration, and really this is what on the ground frontline process engineering excellence really looks like, as it made a real impact on a global scale. That's what I have to share for this presentation. I'll have to take any questions.
Okay, thank you very much. For the final time today, we will take questions. So if you'd like to type them into the questions box, if you have any, we'll just take a pause for a moment. Okay, we have our first question. Did you have an emergency action plan in place when the strike happened, or did you have to get started from scratch after the attack?
No, of course, we have emergency response plans prepared for various scenarios, including security threats. Of course, this was something on a level nobody could have imagined, really. But we do have emergency response plans, so that's what was used to kick off the initial response. And then from there, we went into the restore phase of the activity to try to restore production soon after.
Okay. What is the estimated projected life of the unit, considering it was a repair rather than a replacement?
I presume this is talking about the stabilization columns. Yeah. They were repaired, and the design life used for all the calculations and for the fitness for service assessments was to get another 20 to 25 years of life at least from them.
Okay, thank you very much. That wraps up the questions. So thank you very much on that. It's time to move on. And we have now reached the stage that hopefully you've all been waiting for. It's time to find out the award winner. Before we do that, I'd like to thank all of our presenters today for their presentations and their time. I'm sure you'll agree, a very, very interesting range of presentations. So we'll start with our highly commended entries, and they are from Dow Consumer Solutions and Dow Inc. So well done to everybody associated with those ones. But now to announce the winner, I'd like to welcome back Plastic Energy's Chloe Rigaud. Chloe, over to you.
Thank you very much, and thank you very much to all the finalists for all these very interesting presentations and projects. So ladies and gentlemen, the winner of the IChemE 2020 Industry Project Award sponsored by Plastic Energy is Johnson Matthey. My congratulations to Johnson Matthey.
Well done to Johnson Matthey then, winner of our Industry Project Award. Simon, if we can get you back on the line, congratulations. How does it feel to be an IChemE Award winner?
Thank you. We are really humbled, and it feels really great. And that this is something we share with all our colleagues, which has jointly made such a good effort in doing their best in this achievement. And we're really humbled to get to the finals and to have received this award. So we really thank you very much.
Well, thank you, and well done once again to Johnson Matthey, winner of the IChemE 2020 Industry Project Award sponsored by Plastic Energy. So thank you everyone who's joined us today. Don't forget there's plenty more IChemE Award webinars still to come over the next week or so. They're all free to attend and open to all, so I hope to see you again soon. But for now, goodbye and congratulations to Johnson Matthey.
Thank you very much.